some classification problems for the videos. And we start. So we released the instructions for the final project on the Monday. And the deadline for the first deadline is this Wednesday and today. So up to today, you're gonna read the paper you want to present. And then until tomorrow, we're gonna fix your selections. So when you choose the paper, if you're choosing the paper from, outside from the list, then please read the conditions. You have to read very carefully in the instruction form. And today we're gonna talk about doing some classifications or learning some, doing some classifications on videos. So far we talked about mostly about the images. So in the images, we try to understand the spatial patterns from the image. And as you can see, by looking at this kind of image, you can tell the what's going on inside of this pixels. Uh, but if it is a video, then there's a much more richer context of uh, the pixels that the model can understand. So in this case, if you look at the full videos, then it's actually more like a fighting instead of baseball, right? So understanding the spatial temporal patterns of the video is one of the key challenges of uh, in building the machine learning algorithms for videos. And li like in the images, the classification was the most fundamental and simplest form of understanding. In case of the videos, we are similarly can also do the classification as the most simple task we can do with the video. So we're going to talk about this classification in videos. In case of the videos, the class labels are usually defined as action. The action means a semantic class of spatial temporal patterns in a video. And the action can be characterized by the spatial content plus its temporal dynamics, right? So some example of the action is dancing, cycling, basketball play, swimming, right? These are most simple patterns, simple type of the class you can understand from the video. And we're going to learn how to design the CNNs for doing this class. Some question is how we can recognize the spatial and temporal contents together. So far, we discussed about convolutional neural networks, which are designed for the images. And to understand the patterns in the image, we already know how to understand the spatial patterns. Right? So we can employ this kind of image classification network to understand the spatial patterns in the video, right? So if we treat each frame as an independent image, then we can apply the image understanding CNNs, CNNs for the images. And this will give us some spatial patterns, and that's how we can extract the spatial contents frame by frame. But that misses the temporal patterns, right? That doesn't count. That doesn't count how the pixels are changing over time. So if you want to capture this motion or dynamics of the pixels, then we have to design another component so that we can incorporate changes of the pixel values over time and understand its pattern. So in today's class, we're going to learn some basic ideas of how we can design the CNNs for the action recognition to understand the spatial temporal patterns. And we're going to also investigate a few more methods to incorporate the motion in a video. So we're going to first study with some CNN architectures. We're going to just investigate several architectures of the CNNs and see which one fits the best for the video. So we're going to study basic concept of representing a video and impact of architecture for recognizing video contents. and how this spatial or temporal informations are useful for you. To start our discussions, we're going to first represent the video. So the video, the frame is an image, right? So you can use this notation we used so far. H denotes the height, width denotes, W denotes the width, and it's RGB image, so the channel is width. So each frame is represented by this tensor, Fuji tensor. In case of the videos, we have a stack of frames, right? So we have a stack of images, and they are stacked along the temporal dimension. So in principle, because our image is the 3D tensor, our video should be the 4D tensor, right? Now we have one more dimension for the time. But for the discussions, we're gonna represent the video in terms of 3D tensors. So instead of defining the additional axis for the time, we're gonna stack the frames along the channel dimension. So because each frame is three-dimensional, each channel is 3 dimension for each frame. So if we stack this for the L number of frames, then the total size of the channel will be 3 times L. And for the discussions, we want to simplify this loss function. Right? So the x-axis denotes the temporal axis, y-axis denotes the spatial axis. Right? So given this representation of the video, we're going to investigate several architectures that can process the information from the video. And the simplest form of the architecture is just applying the CNNs, just naive CNNs for the images. So we're going to treat the video as an image. The way that we can treat this is that given the video, we're going to sample a frame, like a single frame, and then we're going to apply the CNN. We're going to build the CNNs on top of this frame. Because we are treating the entire video as a single frame, if this normal image convolution effort can be applied to this. Right? So if you look at this architecture, it's basically applying the classification based only on the spatial context. It can be a reasonable choice because the spatial patterns are closely related to action. It is like playing baseball. Usually, there is some object appears in the scene, back, the base, right? The player. So based only on the spatial content, we can understand about the videos to some extent, but it cannot capture the dynamic as well as the multiple framing information. So one naive extension of the previous approach is that we can sample 2 frames or more than 2 frames. And then what we do is that we just apply the CNNs independently for each frame, which will give us the feature representation of each frame. Then we're going to concatenate these features, which is one feature vector for the video. And then we're going to apply some fully connected layers to do the final classification. This is called the late freedom. We process frames independently up to the representation, and then we're going to fuse it after we extract their features independently. Okay? And for the CNNs to extract the frame-wise features, we're going to share the file. So it's the same CNNs to extract the features of different frames. If you look at this model, and if you compare this with the earlier model, like the single frame model, then it incorporates multiple frames for the classification, and can describe a video better by combining multiple frames. But because we are just treating each frames independently, it cannot discover some true meaningful patterns of the spatial temporal dynamics of the video, right? Because for the features, we are expecting each frame independently. Right? So the alternative approach for that is the early fusion approach. Instead of fusing the frame ID information at a later stage, we're gonna start expecting features uh, spatial temporal at the very first level, right? In this case, we can apply the 3D convolution in the video. So I'm not gonna, I'm gonna elaborate these 3D convolutions later. But for now, just simply consider this as a sort of convolution that operates on the code. Yeah, so this is ignore about this part for now. Just consider that your input tensor is 3 times number of frames, right? The size of the channel is 3 times number of frames. So we're going to apply the convolution filter that applies not only over the three-dimensional RGB channel, but also applies over this number of frames. Okay? So that way we can use the information at the very first layer. And then we're going to process this information over multiple layers. That way we can perhaps discover meaningful patterns, and we can even learn the model to exploit and discover different patterns. That. Right? So we integrate all the information from the very beginning. Then the information used at the very first layer will be processed for later layers. Right? And here we are abstracting all temporal information within some temporal window. Right? And after we use this temporal information, there will be temporal information back to the layers. And there are some alternative hybrid approach. So it's called slow fusion. So we're going to apply these 3D convolutions hierarchically over multiple. The concept is very similar to how 2D convolution works. In the 2D convolution, every convolution layer is basically doing a 2D spatial filtering, right? And each of them has its own filter size. So the receptive field is growing in spatial dimension for the layers, right? We can do a similar thing with the 3D convolution. 3D convolution operates not only in the patterns, but it also operates in the temporal dimension. And we're going to build our convolution unit based on the 3D convolution. Right? So what you can imagine is that the temporal information will be also aggregated over the multiple. And the receptive field in this case is now also defined over the temporal axis. Right? Because the receptive field over the temporal dimension will also grow, like the receptive field grows, spatial dimension. So as you can see in these illustrations, at the very first layer, this temporal receptive field is 4 frames. The first layer performs the convolutions with 4 frames. So the temporal receptive field is 4. But later, you can see that the temporal receptive field grows. So later, so similar to how the spatial features aggregated to the bigger concepts, you can imagine this, you can expect a similar behavior where you start to discover temporal patterns from the very adjacent frames, then you kind of abstract this temporal information to bigger concepts over the long time. So it includes the more and more longer term temporal context in the higher layers, very similar to 2D convolution layers, but it still loses all temporal information before the classification here. Because we are doing the fully connected layer and kind of abstract over it. right? So that's sort of some categories we can consider for designing the CNS for the video. So to summarize, we talked about four different classes. The single frame architecture, which creates the video as a frame. Late video architecture, we treat each frame independently and then combine their features before the classification. Early fusion approach, to combine the multi-frame information at the very first layer and treat this as a sort of limited features at a later stage. In slow fusion approach, that hierarchically combines spatial temporal patterns and then by the classification, right? So that's four different classes we're going to consider, and there are other um, architecture they also consider, but I'm going to skip this part because this is relevant to our. Basically, it's the earlier architecture, so they try to incorporate the multi-resolution field for the classification. So they take the two inputs in two different sizes. Actually, this kind of architecture was discussed when we talked about the pose estimation. In some architecture, we talked about two input ranks, and take the input in different resolution, combine the resolution. But I'm gonna, I mean, so I mean, the, this idea itself is not super relevant to our discussion, just to incorporate like higher multi-resolution classification sense. So I'm gonna skip this part. So if we compare the results of these different architectures, these are the results. So you can see that the single frame baseline, early fusion baseline, late fusion baseline, slow fusion baseline. If we look at these numbers, one thing we notice is that this single frame baseline is performing reasonably well. It means that in this actual classification, there is a strong bias between the spatial pattern and the actual pattern. And intuitively that makes sense. Like, I mean, if I just pick a random frame and show you the frame, and that's guess about the action. In oftentimes you can do a reasonable guess. Right? If it is the riding, for instance, I mean, if it is a cycling, for instance, there should be always a bicycle. Right? So there's a strong correlation between the spatial and temporal patterns. And what this number shows is that indeed, this spatial network alone can do a reasonable job of action recognition. It doesn't mean that the spatial pattern itself is enough. Right? It just tells you that there is some strong spatial bias in the action plan. Actually, in terms of the generalization, it's actually not a good thing. Think about two different classes, shopping and dancing. Right? They both have a strong spatial bias. Right? If you do a shopping, there should be a mall, or there should be at least some shops. Right? So there is a strong spatial bias that if you randomly pick some frame, you would be in a shop. Right? Dancing also has a very strong spatial bias. Right? Dancers have their unique shapes, and dancing move also have a very strong, you know, spatial bias. But also, if you think about the place where the dancing is happening, it also has a very strong bias. It could be either the studio or the stage, something like that. Right? They are performing not at the random place, but at the specific places usually. So both of these shopping and dancing classes have a strong spatial bias. But at the same time, you can dance at the mall, right? So if I show you if the model learn to classify the actions based on the spatial bias, then it will eventually fail classify dancing at the mall, right? So it's not always good thing that your model just leverages the special patterns only for the action classification. It just tells you that your data set, your benchmark for evaluating this action classification has a strong spatial bias. And at the end, what we want is that we want to generalize this model in a way that we can classify the actions for the unseen environment, like unseen context. And for the better generalization, you have to suppress the spatial bias to some extent, right? And if you suppress the spatial bias, right, then you have to learn how to leverage the motion. Okay? So yeah, but at least for this data set, you can see that there is a strong spatial bias. And in some of the baselines, the early fusion and the late fusion, its performance is sometimes even underperformed or just competitive, not particularly better than the single frame baseline. It's because, yeah. So in the early fusion approach, we are abstracting too much information about the multi-frames, right? At the very beginning of the network. So because of that, it can lose even the special pattern. So it can underperform compared to the single frame baseline. In case of the late fusions, it's doing reasonably similar to the single frame model. So you cannot strongly say that it's performing worse single frame if you look at the multiple measures. So it's fair to say that they are doing a similar thing, which means that the temporal patterns are not particularly extracted by the late fusion. Okay? If you look at two frames distant to each other, by the late fusion approach, then the temporal information you can extract from this approach is kind of not strong enough compared to the single frame. On the other hand, if you apply the slow fusion, it performs slightly better and consistently over time compared to the single frame based. It means that, I mean, there is some additional information you can leverage if we consider the motion information video. But at the same time, it also tells us that this architecture is not optimized or the data set is not diverse enough to demonstrate the usefulness of this code information, right? Right. So this is more like a preliminary study of what architectures we can consider for the video classification, as well as what the video classification problem um, is about. It's not only about understanding the motion, it's also about understanding special patterns, and therefore some live baselines can also work to some extent. Okay? And if we apply some large-scale training, so instead of directly training our model for this benchmark, if we pre-train our model for the larger video data set and if we fine-tune the model for this data set, then we can start more significant. I mean, you can also see that the transfer learning also works in this case. So similar to the image case, usually fine-tuning performs better than for training from scratch. If your pre-training has sufficiently large frame data set, the same frame also appears in the video. So if you pre-train the architectures from the larger data set and if you transfer it, then even if their categories are not matching, you can still transfer the user features. Right? So, yeah. And these are some examples of action classification data sets and classification results. So you can see that already by looking at the single frame, you can guess about the class labels to some extent. Running, cycling, something like this, skateboarding. So to summarize, we studied some CNN architectures for video action recognition. The first lesson is that the frame-wise classification performs reasonably well, right? Many features don't recognize. And exploring the motion can further improve the performance. I mean, we cannot strongly say that the motion is like, particularly useful to you based only on this result, right? But it gives us, but it tells us that exploring the motion can be a promise, can be promising at this time, right? And the slow freedom might be the best way to explore this and harness the motion from the video, right? Yeah. So the question is, so even if it shows that exploring the motion can be a promising to improve the active classification results, the question is why exploring the motion doesn't give us a significant improvement. Which choice was suboptimal in the argument? How can you exploit the motion better if the motion really carries? That's the main question. You're gonna study a little bit more. Any questions? Right. Um, yeah. So one thing we suspect from the previous approach is that maybe we exploit the motions in a suboptimal way. There might be something wrong. It, it, it could be the problem in the architecture, or it could be the problem in the data. Uh, we don't know. So the next paper conjectured that motion itself is useful for discovering the feature, the right features for the motion could be difficult. It's difficult to learn. Um, Mainly because first it has a strong spatial bias. So there is a uh, very attractive suboptimal solutions, right? So it doesn't necessarily leverage it doesn't have a like strong incentive to leverage the motion or reducing the loss. The second thing is that, yeah, so discovering the motions, like the optical flow, discovering this explicit form of the motion, because that's kind of tracking or the matching the pixels between the concept frames. And let the model discover these patterns for the classification requires the strong incentive to reduce in terms of the loss, but that's not necessarily required. So it's just matter of difficulty of learning the motion pictures, not the problem of motion. Not right? So that's the conjecture of this paper. So the authors uh, evaluate whether I mean, if we incorporate the motion, the explicit motion like the optical flow as an additional feature for the video, then if the model can benefit from it, like that's the question. So the authors try to see the motion expected externally additional and whether it give us a better performance. If it give us a much better performance, then it basically tells us that exploring the motion is useful, but uh, learning the motion from the pixels is just difficult. Right? So the authors try to incorporate the explicit motion as an additional feature by extracting the motion solution from a specifically they leverage something like optical flow to extract the motion. And then they're gonna treat this motion picture as an additional input for them. Their assumption was that if we just looking at the motion obtained based on the optical flow, it can give us another sort of special temporal pattern in a much easier way for the flow. So, for instance, if you look at these two frames, this woman is moving her arm, and we expect the motions that the motion vector is written this. For instance, we expect this from the ball. And if we compare their x and y axis, then you can see some patterns that moving parts are highlighted with the steady. So by looking at these motions, by using these motions and the external cues, uh, 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 I have to get the quote. So
Recording in progress.
yeah, I'm sorry. So yeah. Uh, yeah. So there might be some special patterns we can discover from the motion if we explicitly incorporate this as an additional input. So and this information, these special patterns extracted from the motion, can be some additional input to the just frame-wise information, right? It just highlights which part is moving into which directions. And uh, by leveraging the special structures of these temporal patterns, uh, we can exploit the additional information in the special temporal dynamics. So the authors tried proposed this kind of two-stream architectures. Um, so given the input videos, we extract a single frame and apply some standard 2D convolution network to extract their spectral pattern, right? The way that it extracts the spectral pattern is that instead of fusing the features, we fuse the predictions between two stream networks, right? So given the input image, the spatial stream network produces the class-wise predictions all the way to the output, right? So in this branch, there's a no consideration of the motion, right? In the second branch, it takes the motion feature extracted from this video, and then it exploits this as an input, right? So this temporal stream network will take this motion feature and then apply the convolution. So these motion features are stacked along the channel dimension. So if we extract the motion feature from the L frames, then L motion features are concatenated along the channel dimension. And then we're going to apply some convolutions to extract their feature, right? Again, in the temporal stream network, we also make a prediction at the output of the class name. And then we're going to fuse these class predictions together to get the final vector, right? So it exploits the motion and content streams separately to incorporate the spatial network. So the benefit is that the first benefit is that using the external motions removes the necessary to discover. So of course, we're incorporating the optical flows in the sort of explicit form of the motion features. We don't have to discover the motion; it's given. So we can only focus on discovering the patterns given in the motion feature. Another benefit is that if you look at this architecture, this upper stream is identical with the image classification, right? So we can leverage this upper branch by using the pre-trained network for the classification of the body. So even if the motion features can be only obtained from the videos, we can still transfer the knowledge learned from the image for the single screen. Right? So you don't have to pre-train this video classification network from the video data. You can also leverage the image data. That's why they just exclusively designed two stream networks. They designed these two stream networks to perform exclusively so that for the one brain you can transfer the knowledge from image data. So if we measure their performance, something like this. So if we compare the, if we only looking at the spatial branch, if we apply, if we train this spatial branch from scratch, the performance is something like this. But if we train, and if we fine-tune this branch from the larger pre-trained model, then the performance improves significantly. It's kind of natural result. If you think about what this spatial stream network need to do. It's try to discover the spatial patterns only, right? And if you train this model for the video data sets, then there are a limited number of objects appears in each video, right? So instead, if we can learn this from the larger image data set, we can leverage the parameters that are learned to discover much richer set of classes, different patterns. And if we leverage that for the video classification, then the generalization. So that's why leveraging the fit-train model will be much better compared to learning from scratch. And if we leverage the temporal convolutions together, then you can see that the performance improves significantly better. So here you see that the different choice of leveraging the model, right? So if we just use the single frame of control, the same as using a single frame, then the performance is limited, but we stack multiple frames. if you use multiple frames for incorporating the motion, then the performance is getting improved much, much better, right? It means that there is some meaningful temporal pattern for the action time, right? So, the performance is getting better. So, it's actually much better compared to the slow field, right? Which means that the motion was not the problem. I mean, motion is useful. That's kind of, I mean, that's clear from this report, right? We leverage the motion information together with the spatial information. The performance improves significantly, like from here to here. It means that there is a very critical information um, in the temporal dimension. We can use it we can use for the classification. So the motion is useful, but the reason that the previous approach didn't get this kind of improvement was because the learning the motion itself from the video. So the architecture was maybe suboptimal. And this is some visualization of learned temporal features. Um, so we visualize the very first layer of its temporal premium. So in this case, so this y-axis is showing you the frame index, right? So each row is the frame, and each column is the filter, right? Because each filter is applied for the multiple frames, you can visualize the filter this way, right? Right. This is how why the filter is. So let's say that your input is H, I, W, N, 3, I, L, right? This is your input. If you apply 7 by 7 convolution filter for this input, what is the size of the convolution? Trigger size is 3 by 3, 7 by 7, because it's 7 by 7 filter. What would be the channel dimension of this filter? It's the same as the input, right? Like this, right? So this is the size of the filter for the very first layer for this input, right? So we can visualize this filter. Each filter is L number of arguments 7 by 7, right? If L equals to 10, then that's what it is, right? This is the number of filters. Each of these 7 by 7 arguments, right? And you have total L number of this L equals to 10, right? So that's how we visualize the filters. So we have total 96 filters, right? And each filter is defined for the multiple frame. And we are visualizing two different filters in space. One for operating on the motion over the x, the other motion over the y. Right? Right. So yeah. I mean, your input was h times w times 3 times m, right? If it is the RGB, if it is the optical flow, it's not 3, 2, right? Because you have optical flow is the motion with the x-axis and y-axis, right? So again, if it is 7 by 7, then you have your filters. Each filter dimension will be something like this, right? And if you choose just one channel from here, it's either the motion, motion filter will be X or Y axis, right? Right? So what you see is that it kind of, if you look at just one frame, like, one filter at the one frame, it's kind of discovering the similar thing with the 2D filters. It learns some special patterns. Like here, it's discovering some horizontal line. Here, it kind of discovers some blobs, right? But what's interesting here is that these filters values are changing over time. It means that it also discovers the temporal patterns as well, right? This filter discovered that the brighter patterns goes to darker, right? And this pattern is showing you that the horizontal part is going above. If you look at this video, right? So some white bar is moving above. The horizontal edges are moving above the time. So you can discover some temporal patterns um, with this temporal scale. So to summarize, we talked about an alternative approach that exploits the separate CNNs for encoding the motion and content. And by separating these two branches, you can first leverage the pre-trained CNNs for the images or the special string branch. And for the motion string branch, you can learn some special temporal dynamics by exploring the motion explicit input. Right? And the performance improved significantly, which means that the motions are indeed very useful for the actual quantification. Right? Any questions so far? Right. So this second paper, it shows us a promising result that leveraging this two-stream network could be useful. The limitation is that we are using some explicit motion as an input, right? So we extract the motion using some algorithm like the optical flow, and then we use that as a input for the temporal network. So because of that, we cannot discover more than the handcrafted feature, right? I mean, uh, I mean, there could be, I mean, while you are extracting the optical flow, you are basically abstracting away many information. Right? It's very clear that you cannot reconstruct the image from the motion feature. It eliminates all the information in the spatial area. It also highlights the moving part of the areas in a very specific way. I mean, just displacement is discovered by this algorithm. So it abstracts too much information about the two frames, right? So relying on this handcrafted feature may be very sensitive to the choice of this feature. And that's basically not the principle of how deep learning works. Right? The power of the deep learning is the end-to-end training. You can learn everything without relying on handcrafted feature or the bias just to optimize the optical function. But now the feature, if we use the explicit feature, that could be a bottleneck for this improvement. So if we can learn the motion features in an end-to-end manner, that will be the ideal. Right? So can we learn the better motion feature from the raw observation? Yeah. So for that, people have explore it. So the next paper will give us some notion of 3D convolution. We already discussed about this 3D convolution a little bit in the last class. At the very end of the lecture, I briefly discussed about this idea of 3D convolution last class. So I'm gonna repeat one more time about how the 3D convolution works. So if you think about these 2D convolutions first, there is a 2D special filter, right? And it's kind of doing a sliding window over the special dimension, right? Right? If we think about the 2D convolutions on the multiple frames, we can define 2D convolutions like this, right? So if we have a L number of frames concatenated, and if we assume that each frame is a single channel, just for the sake of it, then the size of this L number of frames, which are mapped, would be H times W times L. Channel size is the frames, right? And if you apply the 2D convolution for this concatenated feature map, then that'll be the filter should be defined this way. The size of the spatial size should be defined arbitrarily, but their temporal and their channel size should be matching with the input, right? So because the input has a channel of L, we have total L channel, right? In the 3D convolution, you're going to define the convolution filter whose channel size is smaller than the input channel of the input feature. So if we denote the size of the channel of the filter as a D, then the D should be much smaller than 10. Then now because your convolution filter is having a small channel size compared to the feature, you can not only do a sliding window in a special dimension, but you can also do a sliding window in the channel dimension, right? In this case, the channel dimension is the temporal dimension, so it's doing a special temporal convolution, right? As a result, the output map will be also something like this. So each convolution filter will produce the pencil. In case of 2D image, each convolution filter will produce an image, right? If you have a k number of filters, then the output channel will be the k, right? In this case, because the convolution is defined over the channel as well, you retain the channel dimension. So each filter is now producing the image, right? So we can build our convolution neural network based on this 3D convolution. Yeah. So 3D convolution kernels are 3 by 3 by 3, which means that in terms of the spatial size, 3 by 3 convolution, and in terms of the temporal dimension, we are looking at 3 frames, right? And it applies style of 1 in both spatial and temporal dimension. Yeah. We also do a pooling not only over the spatial dimension, but also over the temporal dimension, right? So this way, every operator in this convolution network is the 3D convolution, doing spatial temporal convolutions that everything is, except the finite function. So if we apply this, then you can see that, so we can compare this architecture with different variations. So the first variation is that if you apply this for if you apply TEPS 1, the convolution filters, it means that each 3D convolution is only operating, in the single each frame independent, right? So D equals to 1. So D here, D is the size of the channel for the filter. and we call that as a depth, right? So depth 1 convolution is denoted as a blue, and depth 7 convolution is denoted as purple. And you can see that overall, leveraging the depth 1 convolution is performing much worse. Depths are larger depths convolution, which means that leveraging the temporal information by having a larger by applying the convolution over multiple frames is actually performing better. It means that there is a motion information the models have happened, right? And if you apply the axion classification, the model can improve over baselines significantly better. So compared to just this ImageNet single frame baselines, it's performing much better by harnessing the spatial-temporal patterns in an internet. Right? Yeah. So, any questions? What? Yes. So I think the slow fusion is based on basic frame. Yeah. I have to check again, but in the slow fusion, almost every operator, so there is a many Fluid-Mechanics layers. First of all, many Fluid-Mechanics layers on top of it, and so these 3D convolutions are applied hierarchically but limited for the sphere layer. And maybe they leverage this kind of. I have to check. Yeah. Other questions? So in other words, the slow fusion was sort of preliminary version. It's not. It's similar to how convolution will work. Other questions? Yeah. So, so the 3D convolution can learn. If designed properly, can learn this spatial-temporal patterns in a different manner, and that could be better than leveraging the space method. If we learn this properly, the problem is that the computation becomes more expensive because now we are doing a sliding window, not only over the spatial dimension, but also over the penalty. Yeah. So then you cannot leverage the pre-trained model. So the later works try to improve these parts, which you will learn from the text, right? So to summarize, we talked about the action recognition in today's lecture. So it's basically classification of spatial-temporal patterns in the video. At the end, the important lesson is that if we design the network properly, the motion can be useful. And we talked about different architectures for incorporating the motion, where the 3D convolution, learning the 3D convolution in a different manner is perfectly important. Okay. So I think that's all for today. And please don't forget to feed on the papers by type. And yeah, please read the instructions very, very carefully, right? Because we have about 3 deadlines. You should not miss anything. Yeah, and I'll see you in the next one. Yeah, that's all for today. Thank you.
Recording stop.